for a thesis defense. So I'm sure you all came to see me. No, I know who you came to see, and that's Jessie Ross. I want to, before I start, introduce the people who made all of this possible, and that is Sue Ross and Eston Ross. Without them, we would not be here, so let's give them a hand. Sue and Eston reminded me that all of this started, second phase, when they were in this room in 2013, the spring of 2013, with said Jessie, Jeremiah Ross, JJR, because it was in this room that there were a bunch of students, and I guess I was here too, to encourage all of these newly admitted students to come to UNH. And we got a sucker from Jessie, right? He fell hook, line, and sinker for the lines that were given out. Jessie came in the fall of 2013. I checked his file. I do want to note that when he filled out his form, he did not date it properly, so please be sure that you do that. The other thing that, I'll hold this up. Perhaps you can see this picture of Jessie. Here's Jessie, the quarterback of the team for Holderness School, of which he was the quarterback of the football team. And if you want to see another picture of him, come to my office. He looks like he has no neck whatsoever. And his hair is thin and spiky. There's a seat right here. So Jessie did his undergraduate here and finished in 2017, I think. December of 2017. This is my opportunity to tell one other story about Jessie. He called me during the summer of 2014, and he said, Professor Kinner, Steve, there's a chair over here. You got one? Diane, did you get a chair?
Good, thanks.
Okay. Oh, Wiley, there's a chair over here. Okay. He said, Professor Kinner, what would you think if I said, I'd like to hike the Appalachian Trail in the spring of 2015. His parents thought, but this is what he told me, I don't know if this is true, that I would say, oh, I don't think that's a good idea, and therefore they would have the backstop of not having him go. But I said, what do you think I said, knowing 3/4 of you are students in here, go for it, Jessie! And so he hiked the Appalachian Trail. And that convinced him, I think, of a lot of different things that we won't go into today, but he graduated a semester later than the rest of his class, like Mr. Little, who just came in. We also have on the Zoom today two people, Joe Lewis, who graduated at the same time with Jessie, and worked on the senior project. So it was Joe, Jessie, Wiley, and Kirsten Bailey, who did an oil snare project and kind of, sucked them in a little bit, sucked them into the oil scene. Wiley escaped. Good work, Wiley. And so Jessie started his master's degree in January of 2018. And his co-advisor is, for those of you who don't know him, maybe Kai, you could stand up so everybody can see you. This is Dr. Kai Ziervogel, who is in OPAL and Earth Sciences, at Ocean Processes Analysis Lab and Earth Sciences. And I have the distinct honor of co-advising Jessie along with Kai. The other member of his committee is Professor Tom Ballestero, who is in civil and environmental engineering. The other person joining us on the Zoom today is Jessie's sister, Abby, who is a teacher in Littleton? No.
Northfield, Mount Herman, Western Mass.
Northfield, Mount Herman, excuse me. Oh, I'm so sorry, Abby. And then we are taping this because two folks who are really key to watching Jessie's presentation, Dr. Lisa DePinto, who is the senior scientist of the Office of Response and Restoration at NOAA, and Sue Sapi, who is the science director of the Cook Inlet
Regional Citizens.
RCAC, help me.
Regional
Citizens Advisory Council. Neither one of them could be here today, but Sue helped fund this project along with Noah through the Coastal Response Research Center, and both Sue and Elisa and Kai and I are going to be putting in a proposal based on Jesse's work. And you may say, why isn't Jesse involved? Because Jesse just got a Canals Fellowship from NOAA, our first one at UNH in a few years. And he's going off to romp with Donald Trump in February. So anyway, without further ado, I'll turn this over to Jesse, and he's going to tell you about the role and what's going to happen. He'll talk for about a half an hour, then we'll have audience questions, and then we'll ask all of you to leave, and the committee will stay and talk with Jesse.
Great. Thank you so much for the introduction. Thank you, all of you, for showing up today. I totally thought there'd be 15 to 20 people here if I was lucky. So it's great to see all of you. I'm excited about this research. I'm excited to present it today, and I'm also excited about the direction it's moving over the next few months and years. Like Nancy said, this was funded by a few groups here, University of New Hampshire, CRRC, Cook Inlet Regional Citizens Advisory Council, and the National Oceanic and Atmospheric Administration. But more specifically, some of the people that were already mentioned, I have to thank Sue Soppy for really being the person on the ground in Alaska that made this possible. UNH, the three letters don't mean anything in Seldovia, Alaska. So Sue's expertise really made this, this work happen, and then her efforts to fund 2 field seasons through SERPAC were huge to jumpstart this research. I'd like to thank Kai for taking on an engineering student into the world of oceanography, and a lot of patient emails and explaining fundamental mechanisms that usually a freshman would have learned. So thank you. And then of course Nancy, my view's a little different from the last 6 years of advising. I was in Nancy's office about this time in 2013 hoping to switch majors when she hired me to work in the lab downstairs because her master's student at the time was walking by chance. So I got roped in and spent a few years working on oil spill research as an undergrad, just getting my clothes dirty with Alberta bitumen, and then turned into a senior project. I then was kind of, I moved to Hawaii for a summer to shovel human poop at a wastewater treatment plant, and after 6 days of that, I emailed Nancy and said, hey, is that grad position still a thing for this fall? So, yeah, I do. It didn't take long to say, okay, this research thing sounds cool. Oil's not as dirty as other things. So, and then of course, Dr. Ballestero, thank you for being here and sprinkling advice throughout Greg Hall. I know these names here at Consistent Bay Lab don't mean a lot in this room, but they were really instrumental people. Mike and Hans were the captains of the research vessel, and Dominic Condolero was a scientist at NOAA who really helped jumpstart this research, and Connie also at the lab. That also goes up to Chris Holdery, who's part of the advisory committee, but she was the director of Consistent Bay Laboratory, and many phone calls and meetings to make sure that this research was dialed in to be Alaska relevant, along with the rest of the advisory committee in Alaska. We borrowed sampling equipment from the University of Southern Mississippi, and everything else, slightly as a joke, but kind of truly everything else. Melissa and Kathy, thank you so much for all the fun times. And Missy's probably seen this presentation 50 times, and she's going to sit here and pretend to be interested for one last time and maybe more in the future. But I really appreciate it. So thanks to the friends that are here, and of course my parents for their time today and a lot of time on other days. So here's a quick map of the places that we as this little CRC family have been together in the last year and a half, and it's been huge to go to Boulder, Colorado and talk about oil toxicity, and then have the opportunity to go to Puerto Rico and think about how an earthquake or tsunami could cause an oil spill and what kind of response is needed for that. Many trips to Alaska, but Missy was probably mad about this photo because we weren't eating yet. But we traveled around and had a lot of long days, that's Missy right there with a jacket over her face and Logan. When Nancy's in a good mood, I get to wear her red hat around the airport. And she was looking pretty cool that day too. Had a lot of fun. Kathy.
Oh wait, go back. There's Kathy's grandson.
There's Zachary Monsager.
Our newest E&E. He just came to UNH as an E&E undergrad.
Great. That's Zach. He actually might be here in a little bit. And Kathy actually hand-delivered a microscope to Homer Harbor in Alaska at the beginning of the summer and picked me up from, I had a piece of dirt in my eye at the emergency room, and I didn't realize how much I needed Kathy until she arrived in Alaska, and I didn't know anyone else. So a lot of really good times. Ask Missy what happened on the moped right before this. And that's my cue to get the real party started here. But I just have to thank the CRC for being such a family and a lot of moments like this the last few years. So today I'll be covering marine snow and oil, some background, why this is relevant to Alaska, and then the two aspects of my research, which are baseline particle flux in a region of Alaska, and then some laboratory experiments. So marine snow. What is marine snow? I like to use this video because it's clear these white particles are organic aggregates that I'm referring to as marine snow. So picture this scenario for the rest of the presentation. It's surface forming aggregates that sink down throughout the oceans. This is happening everywhere in the ocean. I like to get that out of the way. I was in I was doing field work with some geologists this past summer that went to a presentation in Anchorage and thought I was talking about snow in marine regions. And they were super let down when they changed their whole days to listen to this stuff. So if you want to talk about snow, go to Elazığ Protect Our Winters event later tonight. But this is marine snow. So phytoplankton blooming in the surface waters as discrete organisms, and then as they bloom and then zooplankton are feeding on them, sticky byproducts are made, and aggregation starts to occur. As they get stickier, then the background sediment and minerals that are also suspended in the water can become incorporated in that, and then eventually get heavier and start to sink. So there's a biological component as well as a physical, and this changes over time and space. So depending on where you are, near shore or far offshore, there's a different export quantity. And the major point here is that the ultimate fate of marine snow is either that it's eaten on its way down through the water column, or it ends up on the seafloor. So mixing that with oil, here's a conceptual model of what happens when oil enters the environment. So there's a surface oil slick here, and then the yellow words show the processes that happen to that oil. So there's spreading, that's like a spreading out over time. There can be stranding on the beaches. Lighter fractions evaporate off after they're exposed to sun, but in this red box are really the processes that could interact with marine snow. So there are submerged processes, whether these droplets are entrained in the water column from physical or chemical dispersion. There are oil droplets that recede from the surface and can interact with marine snow. One of the processes that's fairly well documented and understood is when the oil droplet that's dispersed into the water column mixes with suspended sediment. So here's a schematic of mineral particles that coat an aggregate or an oil droplet, and then that density increases, which would change the fate of oil, that it could end up on the seafloor via mineral aggregation. This has been documented in many spills, and it's also really well studied. It was actually studied at Kensington Bay Laboratory throughout the 80s. Some of the best studies are coming from the same place that I got to work this past year, and it's really well characterized in Cook Inlet. But what isn't as well understood is this aggregation here with biological particles. So mixing with marine snow was first observed in Deepwater Horizon, and here's a photo from 2010 during the response, where responders and researchers were seeing biological aggregates that were really mucus-like and clearly not heavy mineral laden, and then they were sinking and disappearing from the surface. So they were also picked up in sediment traps after and throughout the spill, where there were oily biological flock that made it to the seafloor. And so it's estimated now from research during the response and the last 10 years that up to 14% of the total Deepwater Horizon oil spill ended up associated with biological aggregates. And that was a huge, it sparked a lot of research and a lot of the work that Kai and Nancy have done the last 10 years, but last 9 years. But it was recognized as a potential exposure route because when the oil droplets only mix with minerals, it can't directly enter the food web through predation. So if oil's mixed in with biological aggregates that's already a food source, then that's a vector for different toxicity impacts throughout the food web. And this really highlighted the need coming out of Deepwater Horizon was that this needs to be characterized in places before there's contamination so that responders can make better decisions throughout a response. So in review of kind of the ingredients of how marine oil snow forms, there has to be oil in the environment, there has to be high primary productivity, so a phytoplankton bloom, and then the presence of sediments adds to the ballast weight of these aggregates, so that's how you can get rapid sinking. So that additional weight can lead to higher deposition rates. And the impacts, these are the why behind why are we studying this, why are we all talking about this, and they're subsurface oil. So going back to that conceptual model of where's the oil going, that's what a responder is showing up to figure out is how much oil is in what part of the environment. And so this needs to be understood and recognized also as a potential exposure route. And there's also another degree of consequences creating low oxygen conditions on the seafloor. So whether it's the oil itself or the increased flocculation, that's putting a lot of organic carbon on the seafloor that needs to be degraded. And that can use up oxygen for other species and change the conditions there. So since Deepwater Horizon, there's been a lot of research on how the community's changed, and it's likely different in other areas, but there was a considerable shift in the benthic community after that event. So how does this fit into northern latitudes in Alaska specifically? The Exxon Valdez oil spill of 1989 is kind of an example. So a tanker spilled here. I'm sure a lot of you have at least heard of this spill, but it devastated the southern coast of Alaska in a very persistent oil in a cold environment. But there is a risk for oil spills to happen, and these people in Alaska are very aware of this risk. So saying I'm doing research on oil spill response there makes a lot more sense than talking about it here. And Cook Inlet is the region that I was working in, right in the middle of the red area. And so currently there's a lot of oil extraction and exploration going on in the inlet. This BOEM map on the left shows where there are active rigs right here. There's 16 platforms that are extracting oil, as well as a refinery. And then the red blocks lower out off the continental shelf are under the federal jurisdiction and were recently bid on for future extraction. So they're preparing more seismic work to explore this area. And there's also high transportation. So here's a map of vessel transport by type. And so whether it's an oil rig carrying or an oil tanker carrying crude oil up to Nikiski for refining, or if it's the state ferry that's running off of hydrocarbons, there's a lot of risk in this small area for a spill. And then the other two ingredients that I talked about in the drivers are also there. So satellite images show the high sediment loads throughout the inlet, especially during the spring when there's high snow runoff. And you can see that sediment it's very turbid in the upper inlet, and it's carried out along the western side. And then here's a satellite image of a spring bloom of phytoplankton on the surface. So that checks the box of this being an area that's at risk of marine oil snow forming. Okay, so now moving on to where we come in to look at the baseline particle flux. We really started with the idea that oil spill responders have to be informed of their of how the tools that they use can impact a response. And we worked with Sue to keep this really response relevant throughout with kind of the general question of how could marine snow change the fate of oil during a response or during an oil spill. And then the first step at addressing this larger question is what is the baseline particle flux existing without contamination in Ketchimek Bay, which is part of Cook Inlet. So here's where K Bay is Ketchimek Bay. We used that as a pilot area to explore what was already sinking in this area and look at the quantity, the composition, and how that changed over time and space throughout 2 summers. And just to kind of tie in away from this being a satellite image, there are some major environmental factors that go on doing research in this area. It's a high energy estuary with a 25 to 30 foot tidal range that the water's coming up and down twice a day. The current, so if your boat's in neutral, you could still be moving 5 miles per hour, which is just hard to imagine how much energy is in this system. As well as severe weather coming out of the Gulf of Alaska and large swells that can change very quickly. So another addition to picture this, this is Homer Spit, which divides Ketchimek Bay into Inner and Outer Bay. And it's a severe environment in this. It doesn't look, yeah, I know, it's just, and the lab's over there, so yeah, it's hard. But the point of this photo isn't just to bask in how great it is. It's to show that these areas on the far side of Ketchimek Bay, there aren't stream gauges. There's really little understanding of this estuary compared to some of the estuaries that have been really well characterized on the East Coast. So it is a severe environment. There's a lot of fresh water entering and driving this system, as well as just high energy. So the group, Gulf Watch Alaska, is part of the Exxon Valdez Oil Spill Trustee Council, and they have transects throughout this region. So there's Ketchimek Bay. That picture of Homer Spit is right here, and then these mountains were shown. But they're studying this area really closely to characterize the baseline conditions, and so we were able to meet with Chris Holderried at the beginning of this project to tie into one of their transects. That way, collecting data in 2018, it has some context of how it fits into what did it look like in 2012. Is this a normal year or not? So we picked 3 sites to explore this gradient within Ketchimek Bay as kind of a proxy for understanding the area, and then also have another site out at Anchor Point, which was a totally different beast as far as the energy, but it's also a point of interest of where oil spill responders thought oil would go during a spill. So these are the 4 sites that we focused in on. If you look at the yellow line here, that line is also right here, and now my hike behind the lab officially counts as part of my thesis because I was so excited I could see all 4 of my sites from where I was. This was like 9 p.m. one night. And it's just a large stretch of water, but I feel like this helps dial in that it's not just totally arbitrary points. So at each site, we're deploying surface tethered sediment traps. Right here you can see that there are tubes that have no tops to them, so they're passively collecting particles as they sink from the upper layers of the ocean down to the seafloor. It's free floating, so these buoys are free drifting for an hour to 3 hours and collecting the particles. Here is just a way to help organize what's going on. The mixed layer is the layer of primary productivity near the surface water, and so we wanted to make sure the trap was below that. So we used all that Gulf Watch data to ensure that we were catching particles that were falling out of that mixed layer. And then the total depth to the seafloor was on the range of 35 to 80 meters, depending on which site. So here's the trap that we used with 4 tubes on it. The tubes are pre-filled with a hypersaline solution of artificial seawater. So this creates a density trap. So the idea is that if a particle hits the more dense water here, it's less likely to be flushed out by the less dense seawater. And that held true because I could take these tubes after 3 hours of being in the ocean, check the salinity at the top, and that was still 38 PSU. So that kind of was a mental check that the density trap was working there. And I'll be showing a video from this point on the trap just so you have a perspective of where it's coming from. So you're now on the trap, about to get lowered into Ketchimek Bay. We are adding the tubes onto the trap, and then it gets dropped into the water. And this was a huge win, just to see white aggregates floating in Ketchikan Bay. A lot of people didn't believe this was a big factor in the response community. Biologists totally were not as impressed with this video, but I was happy. And then there were a lot of other things that we ran into, and I couldn't present on this without showing some of the more exciting videos. Jellyfish that stung hands often before I learned to put gloves on. And then this was kind of an awesome moment where Quinn and Megan and Jess were on the boat and helping out that day when this octopus it hitched a ride. And I bothered a lot of marine biologists at the lab by having the coolest video from the whole summer as an engineer. So it was just fun to, I got excited about all the white particles, but then seeing some of the other organisms gave life to the project. Okay, so then once the tubes are brought into the lab, here's a picture showing the contents of the tube. So we're catching marine snow. That tube is then filtered onto a glass fiber filter, which then turned it into a data point. So this was weighed to get a mass of what was collected over that time and in that area of the tube. So the dimensions of a particle flux are mass per spatial area per time, and that's what I'll be reporting the data in. And as a qualitative check of what was going on, so along that yellow line, it was clear that there were high organics. Most after filtering, a lot of the filters were just bright green. There were clearly diatoms. And then at anchor point, there was a much higher mineral load. So just visually, it was clear that something different was going on there. Okay, so here's all the data, and we'll take this bit by bit because there's a lot here. I'd first like to point out that it's split up between 2018 and 2019. The vertical axis shows the total quantity of the flux, and then across the bottom are the sites. So 4 sites, only 3 of each were visited each year, and then the blue bars are showing the total quantity in flux. And the red bars are showing the percent that's organic. So keying back into the idea that the organic route is how oil could mix into or get into the food web. That was part of our analysis. So the first takeaway here was that comparing the sites, so middle and outside were visited the most from 2018 to 2019. There were significant differences in quantity this past year versus the year before. And you can see that clearly following this red line out that flux was considerably less this past year, and we hypothesized that this is driven by freshwater runoff. It didn't rain for nearly 5 weeks through this past summer. So in this range of mountains, if there's not rain or there's less snow, it's likely driving that less inorganics are running off into the water, and then there's less suspended load to be carried down in the flux. And that also checks out. So the other point that I want to point out here is that the red bars are consistent across all sites, and there was not a statistical significant difference either. So both years and all sites had the same organic load, which kind of confirms that phytoplankton bloom was consistent, and that organics that are growing in the water were consistent throughout both summers. And then the last point to take away from this data altogether, that anchor point again qualitatively showed up that it was much higher, but it clearly was about double the total mass was collected in that same parameter. Okay, we also had another opportunity along with SERCAC. So SUSAPI funded this effort to get out to the banks that are offshore. This is Kodiak Island hidden behind the key here. And I just want to point out that this yellow line, it took about 22 hours to get from Homer, Alaska, out to these sites that were called Port Lock and Albatross Bank in the Gulf of Alaska. So very different system here, but trying to take advantage of the fact that we're there with the equipment. And we got really lucky. So here's what it looked like in the Gulf of Alaska. There was not a swell over a half a foot for 4 days, which was absurd. It was a 10-day window. I had help from colleague Alex Ravello, who may or may not be on this call, but it was awesome. We got really lucky and collected a ton of data around the clock. And I just want to point out that I put this picture in here as proof to Nancy that I worked overnight, which is hard to do in Alaska. It doesn't only get dark for about 3 hours. And I also want to say that the people, there were 3 crew members, and they thought I was a research professor until the last day they were throwing taco meat overboard, and I asked if I could keep it in a Ziploc bag. And they said, they're not paying you enough to be here? And I said, no, I'm a grad student. And then they totally burst into laughing and stopped paying attention to what I was saying. So it was a great opportunity to get to these critical areas that, because they're more shallow and far offshore, there's potential for them to be at risk of this because the transport time for oil to get 40 meters in the system versus 2,000 meters would be a lot less. So again, same goal, informed response decision making, and this is part of the work that will move forward. And same data plotted here, or the data applying to the Gulf of Alaska here, but I really want to point out that the scale is significantly different. So these fluxes were about 15% of what was found near shore in Ketchikan Bay. And also the red bars, the percent organic makes up a higher portion of that. So that checks out with other data sets for the area and generally sediment traps that are in deeper ocean settings. Because of the distance from shore, there's less total flux, and then because of primary productivity playing a larger role, the organic percentages were higher. So the next parameter that's worth talking about here is that sinking velocity could be derived from the particle flux measurement in the tube and then a Niskin bottle grab at the same depth. So this is kind of a fun Nancy Kinner freshman year dimensional analysis to come up with a velocity out of this, but I do want to say that these aren't directly measured particle sinking rates. These are velocities calculated from Niskin bottle grab and the tubes. The takeaways from this data set are that there were higher velocities where there was higher inorganics, which agrees with the literature. So the more minerals related to faster rates of collection. That was observed at anchor point, and then also when in 2018 where there were higher inorganics, that was significantly higher velocities. Another takeaway here is that this is the bar for the Gulf of Alaska, and that was on the same order of magnitude as the sites in Ketchikan Bay. And getting back to the response mindset, as far as the time scales, at anchor point, that means that a surface aggregate could get to the bottom in 1 to 2 days, whereas at the other sites, it's more on the order of weeks. So that's kind of what's feeding a response timescale model. Okay, so in summary of the particle flux portion, we quantified the flux, and it's high compared to other areas, meaning that it's a very productive region. And there's also that significant, consistent organic flux throughout the region. Now moving on to a laboratory portion of this, we decided to use roller models, which is a method that Kai has used out at Deepwater Horizon and many other researchers to understand how aggregates are forming and what's the mechanism behind what oil does to a marine snow aggregate. So addressing the question of how does oil mix with surface waters, we added surface waters, and there's actually a thin oil slick introduced into the bottle, which isn't a lot, but the parameters that went into this bottle, it took probably 7 months of us trying to dial it in, and like Nancy said, talking to industry experts, talking to NOAA scientists, trying to make sure that this was as applicable and relevant as we could get with this method. So we're studying aggregation of particles in this water as a function of the addition of oil and then also the addition of sediment from Cook Inlet. And this was conducted from May to June 2019. Here's the tricked out roller apparatus. This is what's often used. So the bottle sits on these rollers and it spins for 5 days, giving a chance for aggregates to grow. But when your advisor says you need an N of 8 instead of an N of 4, you find a way to add things off to the side with zip ties and all sorts of things. And we made it a much stronger experiment by by having a replicate for each treatment condition. And so they would roll on these rollers, and then after 5 days, I'd take them off and do some further analyses. So again, starting with the qualitative differences, the treatment condition is shown across the top. But I'd really like to highlight 2 things. One is that there's clear increased aggregation and consolidation of flocks from the surface water versus the one that has surface water plus oil. So you can see that there's some particles forming here, but they're larger, and with the incorporation of oil, they're larger. And then the same thing, so looking at the sediment control versus sediment plus oil, there's some differences that you can see in the bottom. The next step of this was looking at them under the microscope and taking photomicrographs. So this is related to the particles that were pipetted out of the middle of this bottle. You can see there's some cathocerous or chain-forming diatoms that were loosely connected here. Same with the sediment, it's touching, but it wasn't really held together, whereas both conditions with the addition of oil were much more aggregated and larger. This is what Kathy brought to the lab, but you're now in the microscope looking at UV microscopy, which allowed us to differentiate where the oil cover was. So this is flipping to adding fluorescent or UV light, and then the oil's fluorescing. So all of these are oil droplets that were, it was an awesome tool to use, but we could see where and how much oil was involved in the aggregates. And so then the next step was looking at these same stages, but comparing the fluorescing parts and just the regular pictures. So you can see that both of the non-oil controls had no fluorescing green in them, meaning that there was no oil involved in them. But here you can see that without sediment, the natural surface waters did have significant droplets of oil, and then with the addition of sediment and oil, then there's portions, but they're not necessarily in droplet formation. There's Zach from the beginning. Sorry, Zach. So the next step was to figure out how much oil was there, and that's really the ticket for responders to understand on what order of magnitude that picture is pretty, but what does it mean for how much oil would mix in? And so the next step was to take ImageJ, which is a fairly simple image processing tool, to turn these images into binary photos, and then measure the amount of black pixels and compare the differences. So the top left its binary photo was photo 2, and then the fluorescing of the same aggregate turned to photo 4, and that gave us kind of a parameter of 2-dimensional oil cover, which ranged from 15 to 23%. So that would be just 2-dimensional, what parts are fluorescing, what parts aren't. The next step to try to get at a volume associated with that, we were able to get diameters for each of these droplets, and assuming that they're spherical, you can extrapolate that to a volume. So the program has diameter, we calculate a volume for each of these droplets, and then that's the amount of oil that's associated with this flock, and then if that volume is multiplied by the total number of flocks in the bottle, was equivalent to 0.6 to 9.3% of the total oil that was initially put in that bottle. So that's really the deliverable to a lot of the people on this project, that there's on the same order of magnitude as what was observed in other studies, oil is getting incorporated in biological flocks. The next step of this experiment was filtering. So here are the flocks here. That one of these was shown in the microscopy, but filtering the upper and the lower separately to see how that load was distributed. And so here's just the summary table, and again, we'll take this one significant finding at a time, but the first is that oil enhanced the total solids in the upper, but the aggregates weren't sinking. So that is shown here if you're following with the upper portion of this table. with just the water, it was a concentration of 82 milligrams per liter, but then the addition of oil increased that to 123. And then the same with the sediment added, it was 85 milligrams per liter without oil, and then increased to 125. But it didn't show up in the bottom, and that's why we filtered them separately after the bottles were set for an hour to 2 hours. If they were settling, this concentration would have been higher. And so with just water, it was 162 and almost identical with oil. And then there weren't higher concentrations associated here. So these larger numbers indicate that sediment-induced sinking, which is very straightforward and obvious that putting sediment into a bottle, it sank, but it's cool that it showed up quantitatively as well as qualitatively. And then also the difference between having 690 milligrams per liter without oil, and then oil being in that other treatment only having 488, that raised some question of why would there be less due to the oil, and that was confirmed by some visual analysis that the droplets, like that first picture coated with the orange particles, were actually still positively buoyant, but they were taking clay particles up to the surface. So they didn't sink here as much when there was oil there because they were sorbing to particles and actually floating. So in summary, oil enhanced aggregation of organics and inorganics shown through microscopy, and the filtration showed what agrees with the literature that the addition of sediment leads to faster sinking, and that ballast weight is a necessary part of rapid sinking. And then the order of magnitude, the percentage of the total oil, getting back to the response mindset of how much oil could be associated with organics, is on the order of 0.5 to 9% of the total oil. Okay, so now in summary for everything here, there's a high particle flux in Cook Inlet throughout the region at a depth of 20 meters. There's a significant portion of that that's organic, so 20 to 40% of that is organic, and that represents the pathway into the food web. And this is the oil spill scenario here, is that there are droplets being entrained, some of them are sorbing to aggregates, and the why behind all this are the fish that are below the surface, the pelagic species that are dependent on organic carbon, both in the water column but at the seafloor. And the goal for the responders, this tying back to what our mission was from our first proposal here, was to minimize damage to the environment and then maximize response efforts. And so understanding this exposure pathway really helps dial in what's going on in the total mass balance. So that is all I've got for the presentation side, and thank you so much for listening.
Now from the audience, and then after those are done, we will ask folks to head out, and the committee will stay and ask questions. So fire away. Oh, come on.
Throughout your presentation today, I'm recalling today's class, a lot of the stuff that Professor Nancy is teaching us. I can see that you're mentioning in your presentation, which is awesome, but I wanted to go back to the last slide before this one, because she mentioned today that in Alaska they rely heavily on fishing halibut. So is that a halibut?
Yes.
Picture?
I've got more pictures of halibut I could show you.
Yeah. She mentioned that today, and now seeing that and the effect that on the whole community, it's just a wonderful job that researching.
And this might be a gross simplification that halibut are eating other species, but
yes,
the idea is that that's the rat. Dr. Foster.
So Dr. Foster is the director of the School of Marine Science and Ocean Engineering. For those of you in the room who don't know her, Professor Foster.
Thanks, I learned a lot. And I have questions. As you know, I love sediment and transporting sediment. So if you think about the different locations that you choose, how much do you know about variability of primary production and TSS across each of those transects. So you can imagine that there's a deep water part of the channel. You were probably roughly over the deep water part.
So that yellow line was along the deep trench.
Yeah.
So throughout.
So how much variability is there, and how would you expect that to sort of, your results change based on whether it's current speeds, variations in TSS, or variations in primary production?
I think being able to tie into sites that have that historical data are huge, and they're, because of the way the circulation in the bay drives the sediment load. Each glacier is putting out a suspended load, and by the inner site, there's a much higher surface suspended load. So we had those and expected to see it showing up in the fluxes, but we're thinking because of how mixed the layer was on the inside, that sediment wasn't actually settling out into the traps because it was kind of caught in a really freshwater layer at the top.
So the higher flows, maybe.
Right. So if there's a high spring flow or high, for instance, without rain for 5 weeks, they saw really increased sediment load inside the bay because of glaciers were melting like crazy, and then depositing a lot of sediment inside. But some of my sites that were further out probably didn't feel that signal from the glaciers because it was more water from the western Gulf of Alaska. So yes, there are some major complexities with these sites, both physically and biologically, but I'd love to talk to you more about the sediment specifics.
Oh, interesting, thank you.
Yes, Dr. Jones.
Yeah, Jess, nice presentation. I know this wasn't part of your presentation, your research, but what does oil association with marine particles, how does that affect their like the oil degradation rates? Do you have anything to say about
Yeah, that's a great question, and Kai has a lot more to say on that, but he won't now. But association with biological matter has been shown as a, to quote some of Kai's work, is a hotspot of degradation. So there are bacteria that are either coming from the oil source or from or degraders that are naturally there. So if there's a seep in an area, they're shown higher activity for degradation. And yes, so there are oil degraders living in this matrix. And that's kind of where I thought of where the time scales of sinking velocity would be important. So if particles are transported within a day or two, that would likely have different degradation effects than something that's slowly drifting along for 2 or 3 weeks. But no, I was not keyed into this. And at a presentation in Anchorage, someone raised their hand and said, wouldn't it all be degraded by the time it gets there anyway? Which I stayed away from that. So.
And that was Dr. Steve Jones, who is the Associate Director of Sea Grant and also a professor here. And before he asks a question, that is Dr. Eric Chapman, who is the Director of Sea Grant.
Yes, Taylor.
When you were talking about your roller tests, from what I've gathered, there's many different types of oil. Was there a specific oil that you chose for your roller test, and how would that differ between different types of oil?
Yeah, that's a great question. So we used the same oil that comes out of the Alaskan pipeline, the North Slope crude, which is often transported in the area, but it's not the same oil that would have, if there was a well blowout in Cookin, like that's a different oil. But this is a fairly light oil than what Missy works with downstairs, just to relate back to that. But it definitely would change, and a lot of the studies having oil-specific properties, that was a big part of this step, was seeing if Macondo, which is the type of oil that was in the Deepwater Horizon, if this oil interacted with aggregates the same way. So yes, visually it did, but even the first step of that roller experiment, I was there in the lab hoping it looked the same as the test runs that we did with Macondo oil here at the lab to make sure it worked. So it would change significantly with oil type. Dr. Malley.
I just love what you're doing. I mean, it's amazing how certain principles transcend our field. You know, my mentor was a texture and coagulation guy, you know. So I was really interested in your roller bottles, because in all of environmental engineering, we're always looking for the jar test, the bottle point. So now I'm guessing Kai can backstop you on this. Does it scale up? Is it a good is it a good thing to use in experiments? I mean, we're asked that all the time, right? When we do jar tests and we try to scale them up.
Right.
Is it representative?
Right, and so that, I would say, just because of the size of using 0.8 liters of water, it's significantly different. And I'm not going to say that it directly scales up. But I think because of the parameters we used to make it Cook Inlet relevant, we got closer to it being useful. And I think it is useful as a mechanism of formation. So studying specifically the mechanisms of bacterial activity and the time scale that it's occurring on is useful. But again, this order of magnitude of 0.5 to 9%, I wouldn't go out on a response vessel and say that 10% of the oil is sinking, just from this roller bottle study. But we did work with Roger Prince, who's retired with Exxon, and he had a lot of input on how to make these bottles more useful as someone that's done this for many years. And not that there are some skeptics in recent reviews of this kind of study that we tried to address a lot of that moving forward. But parts of it are relevant. I wouldn't say that the whole thing scales up.
Oh, really great work. Can I add one redirect? Because you know I'm a mass balance fanatic. Did you account for all the oil in your roller bottle? Do you know where it all went?
No. So some of that's another. You're sniffing out the roller bottle downfalls here. But the some of it was lost to the lid, for instance.
Sure.
So this oil is just spreading out.
Sure.
We use glass bottles instead of acrylic because there's less sorption to the walls. But and even Teflon coating the lid, it was still like, okay, there's weathered oil here. So no, I didn't have a full mass balance approach there, but it's part of it. Yeah.
Great work.
Thank you.
Yeah.
Dr. Chapman.
Yeah, just a great talk, and we're really excited for you to go to DC and represent UNH, the Coastal Response Research Center, New Hampshire Sea Grant in New Hampshire as a NAUS fellow. As a quick plug, if any graduate students are interested in learning more about that, please contact me or someone else. At New Hampshire Sea Grant, we can help you learn about how to apply. I'm really excited to see that you connect your research to, how is this going to inform management and response. Can you talk a little bit more about the specifics of how your results or results similar to yours would improve or would maximize the effectiveness of response and therefore minimize damage to the environment?
Yeah, definitely. So this is a pilot study for this area, but with more controversy that gets into the role of chemical dispersants. So as a responder, that's a method of putting this is a different topic to get into, but when they're deciding to disperse oil or not by adding chemicals like in Deepwater Horizon and resulting in a higher load below the surface, then that decision needs to be informed as well. And if there's potential that marine snow is growing quickly and sinking quickly, then it might not be dispersing the oil as much as hypothesized in the dispersant calculation. So the policy ramification, so in policy, which is, I actually spent spring break with Nancy in Florida talking about this exact question here with David Hollander, but the idea of intentionally sinking oil is illegal in the United States because you're impacting the benthic environment. So Canada has considered dumping sediment on oil spills to help the dispersion of oil with just minerals. But this idea of formation with organic aggregates is definitely a major player in policy, and it hasn't been considered in the application of dispersants, or in the US it's illegal to dump sediment on oil, but the idea of a sinking agent and unintended consequences.
So it might inform where you would use the dispersant or whether or not you'd use the dispersants?
It might inform understanding that both in the response, so the timescales here of immediate response, decision making and understanding mass balance, but also what the damage is the months after the response. So if marine snow is an event that's happening, then they would probably look to the halibut bile and see if their pH is in it or not. And that could lead to fishery closures. It could lead to other, understanding that route of exposure could change the policy associated. Yes, Dan.
You go to slide 42.
Yeah.
So I had maybe a minor or a more detailed question, so and maybe a two-part question.
Okay.
So why did you choose the 200 mil and 600 mils like that? Just let's look at top and bottom. And then looking at like in the bay and farther out where it's deeper, looking at these settling velocities, that's going to be relative to how deep it is right out in the bay.
Right.
I guess how does that translate to a response at a certain location?
Right. So, okay. So the first part of your question was why split it up like this. I was using a syringe to decant off that top, and that's as close to the bottom as I could get without resuspending flock that was settled down. So that gave us kind of an upper and lower, but that's the functional answer for that. And then thinking about timescales, I didn't extrapolate too far from the timescales in this study to the velocities that were found in the field. And that's definitely a big player with how fast could it sink. And then going to sediment transport and the idea of advection could be huge. That if these are forming in one area and then actually being carried 10 miles before they're deposited on the seafloor, that could be a major player too. So you're right, but I didn't get into too much of how this would fit into the settling environment. Yes, Sarah.
I noticed in some of your videos that there was a lot of horizontal flow of the
exactly,
aggregates.
the advection.
Maybe, I don't know how that was versus vertical flow. But how did that affect how you were able to collect those aggregates? And do you think you would be able to collect more if you had some kind of entry through the side or?
Right, so if those tubes were normal to the currents, then it might
Yeah.
just be collecting. But again, that's one of the trade-offs with sediment traps is that they're an upward-facing circle, right? And so those particles are streaming by sometimes high velocities. I consistently sampled near slack tide, so it would have more quiescent settling, but that's a huge consideration as far as like the angle of approach and missing some of those particles, as well as the trap free drifting too. So that's being carried at a certain velocity, the currents at another velocity, and right, those videos are capturing the net particle sinking, but it's not like a deep quiescent ocean settling. Yes, Doc.
How many sediment traps did you have to analyze?
So I used this, but the total number was 34 of these sampling events with 4 tubes on them each. Any other questions?
You want to just mention the proposal that just
Yeah. So the proposal is to that Nancy and Sue and Kai are working on moving forward, and I'm going to stay on for some work on this fall. But moving this to look at the toxic impacts all the way down to halibut. So there are people in the Netherlands that we're partnering with to do studies like putting halibut and flounders in actually with oil and marine snow and seeing if they are actively swimming towards marine snow with oil versus sediment with oil. And there's some preliminary data on that, but fitting this into the Alaska case study and moving more offshore to other places at risk, and mixing in dispersants so that getting closer to the policy implications, that's the direction this is headed in. So it's about to open up like this, but the last 2 years were kind of a pilot.
because we know BOEM, the Bureau of Ocean and Energy Management, is very skeptical for Cook Inlet that this was a factor. And so that was the whole idea of Sue thinking we needed to get some pilot data to get some longer term figure from them. Any other questions? All right, Mr. Ross, thank you.
Do you know where it all went?
No. So some of that's another. You're sniffing out the roller bottle downfalls here, but the some of it was lost to the lid, for instance.
Sure.
So
Yeah.
right, this is oil is just spreading out.
Sure.
We use glass bottles instead of acrylic because there's less sorption to the walls, but and even Teflon coating the lid, it was still like, okay, there's weathered oil here. So no, I didn't have a full mass balance approach there, but it's part of it. Yeah.
Great work.
Thank you.
Yeah.
Dr. Chapman.
Yeah, just a great talk, and we're really excited for you to go to DC and represent UNH, the Coastal Response Research Center, New Hampshire Sea Grant in New Hampshire as a NOWS Fellow. As a quick plug, if any graduate students are interested in learning more about that, please contact me or someone else. At New Hampshire Sea Grant, we can help you learn about how to apply. I'm really excited to see that you connect your research to, how is this going to inform management and response. Can you talk a little bit more about the specifics of how your results or results similar to yours would improve or would maximize the effectiveness of response and therefore minimize damage to the environment?
Yeah, definitely. So this is a pilot study for this area, but with more controversy that gets into the role of chemical dispersants. So as a responder, that's a method of putting this is a different topic to get into, but when they're deciding to disperse oil or not by adding chemicals like in Deepwater Horizon and resulting in a higher load below the surface, then that decision needs to be informed as well. And if there's potential that marine snow is growing quickly and sinking quickly, then it might not be dispersing the oil as much as hypothesized in the dispersant calculation. So the policy ramification, so in policy, which is, I actually spent spring break with Nancy in Florida talking about this exact question here with David Hollander, but the idea of intentionally sinking oil is illegal in the United States because you're impacting the benthic environment. So Canada has considered dumping sediment on oil spills to help the dispersion of oil with just minerals. But this idea of formation with organic aggregates is definitely a major player in policy, and it hasn't been considered in the application of dispersants, or in the US it's illegal to dump sediment on oil, but the idea of a sinking agent and unintended consequences.
So it might inform where you would use the dispersant or whether or not you would use the dispersants?
It might inform understanding both in the response, so the timescales here of immediate response, decision making and understanding mass balance, but also what the damage is the months after the response. So if marine snow is an event that's happening, then they would probably look to the halibut bile and see if their pH is in it or not. And that could lead to fishery closures. It could lead to other, understanding that route of exposure could change the policy associated. Yes, Dan.
Can you go to slide 42?
Yeah.
So maybe a minor or a more detailed question, so and maybe a two-part question.
Okay.
So why did you choose the 200 mil and 600 mils like that? Just let's look at top and bottom. And then looking at like in the bay and farther out where it's deeper, looking at these settling velocities, that's going to be relative to how deep it is. Right out in the bay. So
Right.
I guess how does that translate to a response at a certain location?
Right. So, okay. So the first part of your question was why split it up like this. I was using a syringe to decant off that top, and that's as close to the bottom as I could get without resuspending flock that was settled down. So that gave us kind of an upper and lower, but that's the functional answer for that. And then thinking about timescales, I didn't extrapolate too far from the timescales in this study to the velocities that were found in the field. And that's definitely a big player with how fast could it sink. And then going to sediment transport and the idea of advection could be huge. That if these are forming in one area and then actually being carried 10 miles before they're deposited on the seafloor, that could be a major player too. So you're right, but I didn't get into too much of how this would fit into the settling environment. Yes, Sarah?
I noticed in some of your videos that there was a lot of horizontal flow of the
exactly,
aggregates. Maybe, I don't know how that was versus vertical flow. But how did that affect how you were able to collect those aggregates? Like, do you think you would be able to collect more if you had some kind of entry through the side or?
Right, so if those tubes were normal to the currents, then it might
Yeah.
just be collecting. But again, that's one of the trade-offs with sediment traps is that they're an upward-facing circle, right? And so those particles are streaming by, sometimes high velocities. I consistently sampled near slack tide, so it would have more quiescent settling, but that's a huge consideration as far as like the angle of approach and missing some of those particles, as well as the trap free drifting too. So that's being carried at a certain velocity, the current's at another velocity. And right, those videos are capturing the net particle sinking, but it's not like a deep quiescent ocean settling. Yes, Doc.
How many sediment traps did you have to analyze?
So I used this, but the total number was 34 of these sampling events with 4 tubes on them each. Any other questions?
You want to just mention the proposal that just
Yeah. So the proposal is to that Nancy and Sue and Kai are working on moving forward, and I'm going to stay on for some work on this fall, but moving this to look at the toxic impacts all the way down to halibut. So there are people in the Netherlands that we're partnering with to do studies like putting halibut and flounders in actually with oil and marine snow and seeing if they are actively swimming towards marine snow with oil versus sediment with oil. And there's some preliminary data on that, but fitting this into the Alaska case study and moving more offshore to other places at risk, and mixing in dispersants so that getting closer to the policy implications, that's the direction this is headed in. So it's about to open up like this, but the last 2 years were kind of a pilot.
because we know BOEM, the Bureau of Ocean and Energy Management, is very skeptical for Cook Inlet that this was a factor. And so that was the whole idea of Sue thinking we needed to get some pilot data to get some longer term figure from you. Any other questions? All right, Mr. Ross, thank you.